Hi, Algebra 2 fans. I am, at the moment you're hearing this, out of town, and I will see you on Monday, but I want to go through a couple quick things. The sheet that was given out to you actually is going to be used not just for today, but for Monday also. So make sure you keep a good hold of it. And also, this is the beginning of Chapter 6. See what you can do to hold on to all these sheets, because they do represent a very, very good example of the notes. You might as well just call them the notes for the chapter. And if you can keep all of them till the end of the chapter, I think that you have a very valuable review packet with reminders of what things you once did, even though you may have forgotten them. Anyway, yesterday we talked a little bit about this idea of $10,000 being invested when the baby is born, and whether or not it's going to be enough for college. So what we need to do to be more specific about this question, and I wish I could just be with you, because I just feel like it's a great conversation. So because it's pertinent, and it really does. This is a part of real life. So anyway, not just about college either. So what I'm going to do is I want to talk about the what happens in our investment to make that money to make that money change. So let's think about investing this $10,000 and over a span of a few years, and just see what happens to the money as we go from one year to the next. So I'm going to start with year zero, where we have $10,000. And then let's talk about what happens after 1 year, 2 years, 3 years, etc. All right? And I guess I'll just go ahead and stop there. So let's think about, some of you may know about what they call an interest rate. An interest rate is how much money is you earn from your investment over a year. So they're usually an annual rate. So what I want you to think about is, let's take a modest interest rate of something like 6%. So the idea is, if you have a 6% interest rate, what I'm going to do is take my investment and my principal, and I'm going to multiply it by that 6%. Well, 6% is not a number we can really multiply by, so what I'm going to do is make that equal to 0.06. That means the same thing as 6%. And what I'll do is I'll take that $10,000 and I'll multiply it by the 0.06, and what do I get? I get $600. And now my investment is worth $1,600 after 1 year. So I mean $10,600. So without doing very much work, I earned $600 over the course of 1 year. Well, what happens when I continue to do that? Well, first of all, the formula that I'm using is not as useful as I'd want it to be, because it only gives me the amount of money that I added on to the previous year. What might be useful is to get a formula that computes exactly how much I would make in that first year. To do that, what we do is we take the $10,000, instead of multiplying it by 0.06, we're going to multiply by 1 plus 0.06. When I do that, what happens is I'm multiplying the 10,000 by 1, so that 1 gives me the investment money that I had, and then it adds the 600 here. So oftentimes when we're dealing with investment formulas, this is what we're going to do, is we're going to add 1 to the interest rate, and that just helps us compute it. So What happens after we've done this? Well, every year, so after 1 year, I get $1,600, and if I multiply again by 1 plus 0.06, I'm going to get how much after the next year? That's year 2. And then year 3, I'd multiply one more time, and I would just keep doing this, 1 plus 0.06. So I would just keep doing this. This would be the amount of money that I would make after 3 years. And how much does that come out to? That actually comes out to, after 2 years, it comes out to 11,236. After 3 years, I would be moving up to 11,910. I already did these calculations, can you tell? And after the 4th year, I'm 12,625. What I want you to notice is that I only made $600 in the first year, but in the next year I made a little bit more than that. I made $636 from the exact same investment. So I'm going from 600 here, and then I go from here to here, and I end up getting making $636 more. And what happens is that amount of increase changes considerably as I move from 1 year to the next. And then the question is, why is that? Well, the reason why is because the next year, after 1 year, I'm getting interest. In the first year, I'm only getting interest off $10,000. In the second year, I'm getting the interest off $10,600. Some of you may have heard of the term compound interest. Compound interest is when you start getting interest off the interest. For instance, in this, after year 1 going to year 2, I'm not getting interest just on the $10,000. I'm getting the interest on the $10,000 plus the $600 I made the year before. So that's why investments can be really powerful in the long term, is that as the interest grows, your amount of money that you make every year grows accordingly. So anyway, this is just a brief synopsis of how we can set up these equations. In general, if I wanted to find out how much money I could make in many years, I would take the 10,000, and I would multiply it by the 1 plus 0.06 to the power of the number of years. Notice that as I keep multiplying by 1 plus 0.06, I could rewrite that as an exponent. So I'm just going to write this, I'll just say to the y, the number of years. So if it's year 1, then I just multiply by 1.06. If it's year 2, then I multiply by, I use the exponent 2. So here's a good question, is how much money would I make using this formula? How much money would I make in 18 years? Well, $10,000 times 1 plus 0.06 to the 18, well, that's going to equal 28,543. Now, that's a good chunk of change. Likely not enough to fund most colleges for that amount of time, but one of the questions might be, well, can I make an investment that's even better than the 0.06? And some people might. Well, let's take an example. Say you had this amazing opportunity. You know someone that knew someone, whatever. You're going to take your $10,000 and let's go ahead and invest it at say 20%. So what does that look like? That's going to be 1 plus 0.20, 20%, times to the 18th power. In this scenario, if you put this in your calculator, you end up with 266,233. Now, at that point, you're looking at the possibility of going to a more expensive school, not necessarily better, but you can certainly see the impact of the interest rate is pretty remarkable, as well as the impact of compound interest. So this is moving us really far ahead. And if you didn't understand some of this stuff, you might want to go back and just kind of listen to it, because basically what I've done is cover many things that we're going to be talking about in the next week or two. So I moved you ahead a little bit, but I just wanted to give you a general sense for how this stuff works in real life. So if you're somewhat confused, let's just go ahead and move on to some of the stuff that you're going to see for the homework. So moving to the next page. In this next page, we have an exploration. We talked a little bit about this in class. And in this case, what we're going to be talking about is these. Let me see if I can make this screen bigger. Okay. These are called exponential functions, which you're seeing right here. The reason why they're called exponential functions is because we have exponents that have variables in them. So taking a look at this x here and this x here. And it's pretty interesting what happens to a graph when we change the numbers exponentially. So let's take a look at this one. Let's go ahead and see if we can't match graph A. Graph A, let's go ahead and take a few values of x and y, and we're going to be doing this in a moment more officially, but let's just, this is just for practice purposes. What we're going to do is we're going to take a few numbers on either side of the y-axis. So I'm going to choose deliberately -2, -1, 0, 1, and 2. You're going to be doing a similar thing for all these numbers. If I have 2 to the -2, if I put a -2 here, remember that negative is going to flip it, and then it's going to square it. So take a moment and see if you can convince yourself that that's going to be 1/4. Now I plug in -1 for x, and -1 for x, I'm going to get just 1/2. 0 for x, well, when x equals 0, which is the smallest number x can be, I still get 1, because anything to the 0 power is equal to 1. So, and let's keep going until 2 to the 1 power is 2, and 2 squared is going to be 4. So what we need to do is to look for a graph that does this. So we're looking for -2 1/4, all right, and -1 1/2, 0 1, and notice that everyone has a 0 1. That's because anything to the 0 power is 1. And then this thing starts shooting up 1 2. Does anyone see a place where this graph does this? I'm looking at A right now because I can see the 1 2 there. Do I see the 2 4? 2 4, yes I do. And here's the -1 1/2 and the 1/4 for the -2. This definitely looks like the 2 to the x power. So I would match it with that. So you see how that works? Interesting thing happens when we deal with let's look at the graph D and see if we can't match it. So again, I'm going to keep the same values for x. And let's see what happens when if I put a -2 in for, if I put a -2 in for this x, what's that going to do is it's going to flip it and square it. The negative flips it, the 2 squares it, and I end up getting a 4. 1/2 to the -1 becomes 2. Anything to the 0 is 1. That number is going to be the same almost all the time. 1 is going to be 1/2, and then 2 is going to be 4. If you remember the numbers from before, it looks like they're, 1/4, sorry. It's like they were flipped. The y values were switched. Let's see if we can find this graph. Now this graph is -2 4, and take a moment, see if you can find a graph that has -2 4. And I think I may see that here. And let me see. We got the other questions at -1, 2. -1, 2. Yeah, it seems to be working. All right. Well, this graph is, this is 1/2 to the x. And you notice that this graph, sorry about that, this graph, if looking from left to right, is going down like this. Whenever something is getting less and less and less exponentially, we call this a decay graph. Anything that is like graph A, that's going from left to right, gets higher and higher and higher, which you would like your investments to do, right? We call that growth. So what made a growth graph a growth graph? What made the decay graph a decay graph? Well, look at the decay graph. The base number is 1/2. Anytime the base is less than 1, we get what's called the decay graph. And a decay graph is something that often happens. We see this in science with radioactivity, things like that. There are certain things in nature and in business which decay. Another thing is when you buy things in business and they lose value, oftentimes it's described exponentially too as a decay function. But growth function, the difference between the growth and decay is that in this case, the base is greater than 1. So if the base is bigger than 1, then we know we have a growth curve. So exponential curves largely look the same. They're either going up or they're going down. If they're going down, we call it decay. If they're going up, we call it growth. Let's look at the graphs. Just for practice purposes, let's look at B, C, D, and F, and let's see if we can identify them as either growth functions or decay functions. So take a moment, look at B, 3 to the x. 3 is greater than 1. So we would expect that to be a graph that goes higher and higher and higher. We'll call that growth. E, conversely, this is 1/3, which means that the numbers are being multiplied by 1/3 each time or cut by 1/3 each time, which means that this is decaying. It's getting smaller. Similarly, for C, growth, and F, decay. On your homework, you're going to have a couple questions. They're going to be asking you whether a function is a growth or a decay function. Basically, the answer to that question comes from what the base is. If the base is bigger than 1, it's going to be growth. If it's less than 1, like a fraction, 1/3 or 1/4 we're seeing here, it's a decay function. So if any of that didn't make sense, go ahead and play it back because that does have an impact on the homework that you have for tonight. So let's go ahead and let's move to the next page. Oh, sorry about that. Before we move to the next page, I want to go to the bottom here. And I think I already answered the answer to exploration 1, but one of the things that we want to talk about in terms of the exponential graph, the exponential graphs, the exponential functions, is let's look at this graph A. One of the things you'll notice is that is that as we go to the left, the number gets smaller and smaller and smaller. But despite the fact that it gets smaller, it never gets to 0. Whenever we have a line that gets smaller and smaller and smaller but doesn't actually become 0, we call that line that it approaches an asymptote. So an asymptote is a line, in this case the asymptote is the x-axis, is a line that a graph approaches but never touches. So no matter how far to the left that graph goes, it never touches the x-axis. Same thing is true here with graph D, is that the graph goes to the right far and far, far. No matter, you keep cutting it in half, cutting it in half, cutting it in half, cutting it in half, but it never becomes nothing. I think that's if I gave you a bar of gold and you kept cutting it in half, well, actually that's kind of, you get into the atomic thing. But the idea is that if you take something and you keep cutting it in half, you never get to zero. You just keep cutting it in half. It gets smaller and smaller. So here again, the x-axis is an asymptote. And this is one of the characteristics of an exponential graph, is that it has an asymptote, a line that's approached by the curve but never touches. And what else do we notice about? What else do we notice? It says in expression, is it possible to graph? Is it possible to graph for the graph of an exponential function to have an x-intercept? Explain your reasoning. Well, the reason it can't is because if it's an x-intercept, that means that b to the x would have to be equal to 0. And there's no value that I can put in for x. The lowest value that x can be is 0. And anything to the 0 is 1. So we cannot, there's no way that we can get this thing to cross the x-axis. And that's why we call that place an asymptote. Let's move to the next page. We only have a couple more things to do, and you should I am so tired of going down. Able to do your homework. This is a quick review of what I just talked about. This is a graph of a growth function, right? So with this information here is telling us that exponential functions are either growth or decay. In this case, it's a growth function if the base here is bigger than 1, and we just spoke about that. So it's probably not. I'm not going to belabor it too much. One also interesting aspect of all growth functions and decay functions is that they all share this point 0, 1 on the more basic. What did I do here? On the more basic on the basic functions. So the parent function, I should say, always has a 0, 1. Okay, and let's go to the parent function for decay function. And again, if you notice, going from left to right, we're getting smaller and smaller and smaller. And this is, and that's based on the fact that b, it's because in this case, b is between 0 and 1, which means it's a fraction. So b is a fraction less than 1. All right, so let's not belabor that point. If you wanted to zoom through that little discussion, I guess you're fine. I just want to put it in a plea. Let's go. So this is the first part of your homework is going to be several questions where you're going to first determine whether something is a growth function or a decay function, and then you're going to graph it. Now, it just so happens that we've already seen this particular graph, but let's go ahead and let's put some numbers in here for it to graph. Okay, so let's stick with our usual numbers here. So this first one is going to be the y equals x to the 2. We've already done this, so let's just watch it again. See if you can remember the values that I'm using for x. -2, -1, 1. Sorry about that. 0, 1, and 2. So x to the negative, 2 to the -2, the negative, remember, 2 to the -2, that negative flips it, so we get 1 over 2 squared. That's our 1/4. Similarly, 2 to the -1 just becomes 1/2. Anything to the 0 is 1. 2 to the 1 is 2. 2 to the squared is 4. And we graph these points. And let's see what we get. -2. Yeah, 1/4. So that's going to be, approximate that. -1 is going to be 1/2. 1, 1. 1, 2. And 2, 4. So you can see the graph is going higher and higher and higher. Again, we say asymptotic on the x-axis. It keeps getting closer and closer, but doesn't touch. All right, let's do the other graph, the b. Let's go ahead and what is that? 1/2 x. I'm sorry. So this is y, or f of x. Y equals 1/2 to the x power. Again, -2, -1, 0, 1, 2, and to the -2 is 4, as I explained earlier. 1/2 to the -1, just flip it, you get 2. To the 0 is 1, and then we just, again, this is just the reverse of the numbers upstairs above us. So we're going to have so let's go ahead and graph these points. -2, 4. And -1, 2, 0, 1, 1, 1/2, 2, 1/4. And so what you're seeing is a graph kind of like the one above, but it's going, instead of getting bigger, it's getting smaller going from left to right. Again, that's the x-axis is called an asymptote. Alrighty. Now what I'm going to ask you guys to do is move to this page, and I want you to see if you can't graph these points. I'll go ahead and start you off with the first one. All right, I know these are going to be a little bit trickier, but I'd like you to try to graph them on your own. If you want to pause for a moment and see if you can't figure out this graph, I think that would be a great idea. If you feel like you have no idea how to do it, then just go ahead and don't pause. But let me go ahead and I'll start off. -2, -1, 0, 1, 2. 4 to the -2 is going to be 1/16. 4 to the -1 is going to be 1/4. 1, 0, 1 again. 4 to the 1 is 4. And then 4 squared is 16. Now this doesn't look like it's going to fit very well on our graph, but let's go ahead and get a sense for this. -2, -16 is going to be very, very, very close to the to the y-axis. -1, 1/4, it's coming up a little bit, then all the way here, 1, 4, and then it just shoots off into space way up here somewhere. All right, so this is a very, 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 very steep graph. That's because the base is a pretty big number, 4. All right. So there we go. Let's. This next one, I think that is worth watching me do because the numbers are crazy. I know how much people love fractions, but again, -2, -1, 0, 1, 2. To the -2, what's going to happen? The -2/3 to the -2 is going to be the same thing as 3/2 squared. The negative flips it, and I get 9/4. Yuck. But anyway, 9/4, which is equal to 2 1/4. If I put a -1 in, it just flips the graph to 3/2, which is 2 1/2. Again, 0, 1. Now this is where things flip. I go, 1 is going to become not 9/4, but 4/9, which is about 1/2. And then the next one to the 2/3 squared is going to be 4/9. Not 4/9. It's going to be, sorry. Ooh, I'm sorry. I messed up there. Did you guys catch it on here? To the 1 power, it's just going to be 2/3. So, and this is where we get 4/9. Okay. So let's see what that looks like for a graph. Again, graphs are approximate, so you don't have to get the exact place. But -2, 2 1/4. -2 is 2 1/4, somewhere like this. -1, 2 1/2. -1, 2 1/2, a little bit higher. um, 0, 1. Oops, there's a mistake there. I don't believe that 3/2 is 2.5. Somebody catch that an hour ago or what? Sorry about that. So that's going to be 1.5. So let's regraph that point. It's going to be -1, 1.5. There we go. That makes more sense. Somewhere in here. Get out of here. And then 0, 1, and 1 is going to be 2/3, and 4/9 is going to be just a little bit less than looks like it'll be like a little bit less than 1/2. So anyway, we get the idea. This is a pretty not so steep curve, and it's because the base is less than 1, it is a decay curve. All right, so I'm going to ask you guys to go to the next page and do the best you can graphing these two. Now, if it really helps, 0.25 is the same as 1/4. So you can use either one of these numbers. 1.5 is the same as 3/2. So if you want to use fractions, you can. And let's go ahead, pause, do your best to graph these, and come back in a moment and see if you did a good job. Okay, so these are your two graphs that you hopefully came close to. Again, we need to approximate sometimes. I mean, graphing 1/4 or 1/16 on this graph is not so easy, but this is my table of values for 3, and it gives me a decay graph. And with the 1.5, which is 3/4, that's going to be a growth graph. It's pretty slow moving up. Again, approximate the 4/9 to be a little less than 1/2. The 2/3 is 2/3, I guess, and the 3/2, you can do that one. But anyway, just try to approximate it as best you can, and I think things will be fine. So let's go ahead and move to our last topic for the day. I know you guys are anxious for that, so let's get to it. A real life type problem. So this is our last example. So part of your homework, you have a few questions where you have to describe whether something's growth or decay, which basically means is the base a fraction, less than 1, or is it bigger than 1? Bigger than 1 is growth. So now what we're going to do is actually apply. We've already applied these to. We've already applied this to in the first page of this, or the beginning of this discussion. But what I want to talk about is one of the things that we talked about when we created our equation in the beginning of this talk, is we talked about the idea of using a 1 plus the rate. The 1, what the 1 does when I distribute is it gives me the amount that I start with. And then what the R does is it gives me the money that's being added to what I start with to tell me how much money I have at the end of the year. Now, this is for growth. This is for like an investment model, the first one, the growth one. But we also have a decay model where we try to take the number and we set it up as a 1 minus a rate. So I'll show you how that works right now. So in this case, I showed you a growth model at the beginning. I'm going to show you an exponential decay model right now. So here, and I keep hitting these buttons wrong, but anyway, a real life problem. The value of a car, Y, in thousands of dollars, can be approximated by the model 25 times 0.085 T, you see that over here, where T is the number of years the car was new. Okay, so let me show you exactly how this works. The 25 represents the original cost of the car, $25,000. And what we need to do, because this is a decay problem, we need to rewrite the 85, that 0.85 as 1 minus something. So what is 85 as 1 minus something? Well, some of you may figure out that that's the same as 1 minus 0.15. Think about it. Is that correct? Just trying to make it match. Instead of putting an 85 in there, I wanted to write it as a 1 minus. When I write it in this way, the 0.15 represents the 15% loss in value. Okay? What was the original amount of money? It was 25, and this Y represents how much the car is going to be worth after so many years, which is going to be represented by this value T. So clearly, we're going to need our calculators for a lot of this stuff. So it says identify the annual percent increase or decrease in the value of the car. Well, in this case, it's a 15% decrease because, again, this is because the base is 0.85. It's a decay function. We're talking about something getting smaller. So, and it's minus, of course. I think that's probably even the more to the point. Okay, so one of the things I want to show you right here says the percent decrease, reasoning quantitatively, the percent decrease is 15%, tells you how much value the car loses each year. The decay factor is the 0.85, tells you what fraction of the car's value remains each year. Can you guys give me like 5 minutes? All right. So anyway, to do this real life problem, and you have only one on homework, is you need to translate the value inside the parentheses into a 1 minus or a 1 plus type number. So whatever it is, there's going to be a 1 in the front, plus or minus some number that equals that 85. And you'll see that in the problem. So it says estimate the value of when the value of the car is going to be $8,000. To do this question, you will need to put this in the calculator. And if you actually, I wonder if I can do that in front of you. Here's my calculator. I guess I need to put on a video. There it is. So I don't have a. So what I'm going to do is, you can see the screen. Let me see here. Turn it on. Go to y equals. I'm going to delete that mess. And what I want to do is put in the equation that I have. I'm going to pause. Oops. Okay. All right. I guess I didn't turn on the video. So anyway, I turned on the calculator and I went to the y equals, and I'm going to put in the calculation right now and then go back in here and come off pause. But give me a second. I don't know what happened there, but it looks like it just it just stopped working. But first off, let me just show you how I put the equation in. 25 times 1 minus 0.15 to the x. And then my little shortcut is I found it on Zoom. If you arrow down far enough, you can get this thing called Zoom Fit. And that's actually what I use, Zoom Fit. Press enter, and hopefully we'll get a good graph. So from here, what I want to do is find out, now this, in this case, x is the number of years. So the x-axis is the number of years. What I'm going to do to find out the answer to the question about when is it going to be worth 8,000, I'm going to go just use the trace button. And right now, the trace button shows me at 25 years. What I'm going to do is, and the x value is, I'm sorry about that, 0 years. What I want to do is, it's showing me the present value of the car. And so what I'm going to do is I'm going to push the left arrow. And as I push the left arrow, you're going to notice that the x value is becoming, it's becoming smaller and smaller. Oh, a minute here. I think I may have to move up a little bit. Okay, so, all right, x is the number of years. I'm sorry. Y is the value of the car. So the Y value of the car at so I'm looking for when the value of the car is going to be. I think it's at 8,000. So right now the Y is at 10, 9, 8. Oop, went a little bit too far. And right there, that's pretty close to 8. So the Y value 7.9 is approximately 8, which represents $8,000. And when is that going to happen? Well, look at the X value. The X value was where is the time, and that's going to be 7 years. So that's how you're going to do the one question that we have on the homework regarding the problem. So on the homework, you're going to create the equation. And if you need to, come back and look at what we did on this so that you'll have a better idea what's going on. So to estimate the value of the car, when the value of the car is going to be that $8,000, you just put this equation into the calculator, and that's and adjust it till you get that 8,000. The question that we have for your homework that's going to be like that is it's going to be right here. I guess I love this little video thing, so let me just go ahead and show it to you. It's right here. It says the value of a mountain bike is approximated by that equation, and where t is the number of years since the bike was new. So it says tell what the model represents exponential decay or degrowth. Well, the 0.75 is the answer to that question. Identify the annual percent increase or decrease. Now, in this case, the question is, can you figure out how to write 0.75 as a 1 minus number or a 1 plus number? I would say 1 minus something would work. So give that a shot on this one. And then again, you're going to use your calculator to make your estimate for C. And that's pretty much your homework. And that's and it's posted right now on Big Ideas. And I wish you guys the best, and hope that this was helpful in at least giving you an introduction to exponential equations. And I will see you on Monday. If this became totally the wrong language for you, please feel free to come to help session on Monday morning. But I think that if you really do, if you do take some time and listen and re-listen to this, you should come away with a pretty good base understanding of an exponential functions. Take care, you guys. I'll see you on Monday. Bye now.